Next, we're going to start with the weak base, strong acid titration. So this is going to show the titration of 40 mils of a 0.100 molar NH3 solution with 0.100 molar of HCl. Because we're dealing with the weak base, we're going to be titrating with the strong acid, that is HCl. And so we're going to have our pH still, and of course volume of NaOH to show our titration curve. Number one, we're going to have our initial pH. We, of course, is going to be higher because we're dealing with a weak base. And if we're dealing with the weak base, we know it has the ability to produce OH minus, and therefore will have a Kb value. If you have a Kb expression or value, you can go ahead and get a Rice table, get an OH minus concentration, go ahead and get your pOH, and of course, get what we're looking for, which is the pH for the initial portion. Next, you should see a gradual decrease, not increase like I wrote here, decrease, right? And as you can see, this titration curve is going to be the exact opposite of a weak acid, strong base titration curve. So we're starting off initially, we're in our buffer region now, and we're seeing that gradual decrease. And so what is the buffer region? The buffer region is going to be made of buffer components. That's going to be our base, which is NH3, and its conjugate acid, which is NH4+. If we have a buffer region, that means we definitely can use the Henderson-Hasselbalch equation to get pH. Also, at the midpoint of that buffer region, it's going to give us the pKa value, because that's when the pH is going to be equal to the pKa. As we continue on, the pH at the equivalence point is going to be below 7.00 or below neutral. Why would the pH be lower than 7? Well, because all of the base is going to be used up. So all the NH3 is going to be used up, and of course it's going to equal to the amount of HCl that you added. What's going to be left over? The conjugate acid. And that conjugate acid has the ability to react with what? React with water. And once it reacts with water, it's going to form H3O+. Because it forms H3O+, that's going to allow for the decrease of the pH as we see here. And then finally, if you continue to add excess acid, you're going to get a slow decrease of the pH because, of course, you're making things more acidic. We can do the same thing and use our weak base, strong acid titration curve to find the pH at every single point. So number one, in order to find the initial pH, you're going to use your Kb expression to find the OH minus concentration. Once you find the OH minus concentration, you can get the pOH. Once you have the pOH, you can go ahead and get the pH. And then finally, if you want to use that buffer region, because we're dealing with buffer components, then that means we're going to have our NH3 and its conjugate acid be able to use that ratio to our advantage and use, of course, the Henderson-Hasselbalch equation. So that means if we're changing our volume because we're adding our HCl, we need to make sure that we're going to use a Rice table that shows that the HCl is going to be used up. What's going to be left over is going to be your moles of your base and the moles of its conjugate acid. Those new amounts can be used in the Henderson-Hasselbalch equation so that you can solve for pH. And of course, you need pKa here. So you have to use your Kb to find Ka, and then use your Ka to find pKa. Then when we get to the equivalence point, again, you are adding in a certain amount of HCl. That's going to be the exact same amount that we started with. So we had 40 mils of NH3, and we're going to be adding 40 mils of HCl when we're at the equivalence point. They're going to be equal to one another. So you're going to get your initial amounts, add those into a Rice table. Your NH3 is going to be used up here, and so you're going to be left with your conjugate acid. Once you have your conjugate acid from the Rice table and its moles amount, you're going to divide it by the total volume. When you have your concentration at equilibrium of your conjugate acid, now you can go forward with your Ka value and your Ka expression, and then once you have your H3O+ and you solve for that, you can go ahead and get your pH value. And then finally, after the equivalence point, if you're going to continue to add excess HCl, then you must have your initial amounts for each of your species. You're going to complete a Rice table. This time again, your base is going to be used up because it's past the equivalence point. What are you going to be left with? You're going to be left with the excess moles of H3O+ that you have been added in. Once you have your moles and divided by the total volume, then you're going to get your concentration of H3O+. Once you have your concentration of H3O+, you can simply go ahead and get your pH value. For all the curves so far, we focused on that equivalence point to help us understand whether the moles of our analyte and our titrant will be equal to one another, right? Of course, for us, we cannot basically look at calculations from just something that's clear, so we use acid-base indicators. An acid-base indicator is a weak organic acid whose color is going to differ from that of its conjugate base. And so that color change is going to happen over a very specific narrow pH range depending on the type of indicator that we have. And it's all based on that conjugate acid and of course its conjugate base. So let's go ahead and talk about it. We can look at this weak acid here, which is like a red color. It's going to be mixed with water to produce in equilibrium H3O plus and its conjugate base, which is a completely different color. So the Ka expression will be its products divided by its reactants. And of course, we can go ahead and call out a ratio, and that ratio we know between the weak acid and its conjugate base is directly proportional and related to the concentration of H3O plus. Now, of course, if we didn't want to just focus on H3O plus, we can take the P-scale version of this and show that the ratio, which is now the conjugate base divided by the weak acid, is directly related to the pH value. And so this table kind of shows that. It has pH values at the top and different indicators here. So one that we're mainly focused on is phenolphthalein. Phenolphthalein, as you can see, has a colorless, it's colorless here, and then it goes to like a darker pink over the pH range of 8 to 10. We also see things like bromophenol blue, which has a pH range between 3 and a little bit before 5. Methyl red, pH range between a little bit over 4, a little bit between over 6 here. And so again, we focus on the pH range, we focus on the conjugate acid base that we have, and then we make sure that our pH equivalence points are only going to be very close to that equivalence point. And we want our indicators to be close to the equivalent point, or at least about 2 pH units around the equivalence point. Why does that matter? Because we need that color change to signify that we have ended the reaction. That color change is going to show us that we can end the titration, and then we go through calculations to show that at the equivalence point, the reaction has ended as well because everything's in equilibrium. Using the Henderson-Hasselbalch equation, we can actually solve for pH by taking the pKa plus the log of that ratio, okay? So if we're going to have the log be a negative number, then you're going to be in the acid color. If you have the log going to be a positive number, then you're going to be with the base color of the indicator. And if so, we kind of just take a range of the pKa plus or minus 1. That's going to give us the overall narrow portion that we're looking for when it comes to these indicators. Sometimes you will see indicators that are like pH units of 2 or more, but again, we normally see plus or minus 1. Let's look at the indicator here of bromothymol. Okay, so this bromothymol blue here. As you can see, we're looking at a pH range between 6 and 7. And of course, this is more specific. And when it's going to be a pH that's less than 6, we have a yellow color. Here's the intermediate color. And then when it's going to be more than 7.6, then we have this blue color. And so that's just an example of that kind of indicator. We also saw situations that we saw in lab as well, where it's important to use multiple indicators to have different pH ranges. So sometimes you're going to need an indicator like phenolphthalein. Sometimes we'll need an indicator like methyl red. Here are titration curves, just like the titration curves you saw before. Strong acid, strong base, weak acid, strong base, and weak base, strong acid, okay? So here are all the titration curves. And in the red here, we have like the pH range, it's kind of reddish pink, the pH range of phenolphthalein, and then here, and the orange, and then yellow here, or red, orange, yellow, we have the pH range for methyl red. As you can see, for each titration curve, we also have the equivalence point. And the goal is that you want to use an acid-base indicator that is going to be suitable and near that equivalence point, or if anything, can capture the equivalence point. So of course, the equivalence point is here for this titration curve, but we can see that our phenolphthalein is above it in this top portion, and our methyl red is below it in this bottom portion. So even though they're not exactly at the equivalence point, they still have the ability to be suitable because they are on the vertical line. So you can use phenolphthalein or methyl red for this one here. For this titration curve, as you can see, the equivalence point is right directly where phenolphthalein is. So I would choose phenolphthalein for this particular titration curve. For this titration curve, as you can see, the equivalence point is going to be with methyl red. And so, of course, I would choose methyl red for this equivalence point so I can capture my titration properly. And this is some sort of the behind the scenes things that a lot of the lab managers work will be doing, because they have to be the one to kind of double check all of the indicators that we use in our lab to verify that they can actually be usable and can get good result and outcome.